Ladies and gentlemen, brace yourself. You are about to dive headfirst into the swirling vortex of the transformer architecture and code language models and their full multimodal glory. This ain't your grandma's knitting tutorial, folks. This is the digital equivalent of juggling flaming chainsaws while riding a unicycle on a tightrope. It is like trying to solve a Rubik's Cube in the middle of a roller coaster ride. It's like, well, you get the idea. So if you're an absolute beginner, you might feel like you've accidentally wandered into a quantum physics convention. But don't worry, hey, don't worry. We'll try to keep the mood light. And even as your brain does somersaults trying to keep up, never mind, buckle up, grab your popcorn, and let's dive into the deep end of the coding pool. And then I would like to show you an absolute outlier. And this absolute outlier is here by a company I didn't expect it. It is Salesforce. Salesforce Research Asia started in September 2021 with Code T5. Very interesting model. But you know what? They came up now in May 2023 with Code T5 Plus, an open code large language model for code understanding and generation. So this is now the advanced model, May 20, brand new for me when I'm recording this. And I would say, have a look at the training data and the architecture of their transformer architecture. So here we go. What is the data? Now in the pre-training data set, they enlarged here the specific set that they used with a recently released GitHub code dataset. This is now available on Hugging Face. This is fantastic. They select 9 programming languages: Python, Java, Ruby, JavaScript, Go, PHP, C, C++, and filtered the dataset only by permissively allowed licenses and files with 50 to 2000 token. They cleared the dataset. Yes, yes, yes. And this is interesting, they also have instruction tuning. And they apply over 20,000 instruction tuning data in a specific code. And they use here this self-instruct mechanism I have a video on. They use here another LLM that generates here the instruction fine-tuning data for them. This is OpenAI's Text DaVinci 003, one of the best models currently for this task. And they include here the task instruction synthetically, the inputs, and of course the expected output. So the input-output pairs plus the instruction is their synthetic self-instruction fine-tuning dataset. And they call this Instruct Code T5 Plus model. So whenever you read Instruct Code T5 Plus, you know this is here from OpenAI synthetic dataset generation. To show you how this looks, very familiar, you know this. If it's SQL, Python, never mind. You have an instruction. Let's take this here on the right side. Optimize the given Python program to improve the speed of execution. And this is the training data set. So you have an input that is not optimized. And then you have an output of a code sequence that is optimized for speed of execution. And you have hundreds and thousands of examples, so the system learns how to optimize code that is given and present to you the code sequence of hundreds or thousands of programmers that optimize this specific code sequence. And SQL queries, yes, you know this. It doesn't depend anymore where your data is. Everything becomes interconnected in a data mesh. Great. Now, the task that they pre-trained Code T5 Plus on is interesting because they have now a lot of tasks, and I would like to show you the beauty of this system, what makes it so different to the other system. So they train Code T5 Plus, a mixture of pre-training tasks. They have this causal language modeling I just showed you before, the contrastive learning, the classical way, and they have a text code matching. This is the very first beginning of the video where I showed you the comparison GPT-4 to Star Chat that is based on the Star Coder base LLM. So this text code matching is interesting for them, and they do this on an unimodal code and a bimodal code text dataset. Great. Now, I will show you in a second that this is a model that has an inherent beauty and a powerful structure no other model has. No other GPT model can have, because the way they built their LLM. Now, if they take now the complete architectural side of a transformer, you have an encoder and a decoder model. So the Code T5 Plus can support the code generation and the code summarization. You remember on the left side, you have the encoder stack, and on the right side, you have the decoder stack. And you can easily use it as a decoder-only model. This is exactly what the GPT models do for autoregressive generation tasks, such as code completion. In code completion, this is the strength of the GPT models, because there is absolutely the focused task of autoregressive generation of code. And finally, now if you have both, and here only the decoder, you have here the option of only an encoder model, which they, of course, use here for the neural searchability, or if you look here at Asia from Microsoft, at the retrieval task, as they call it. So you can run this Code T5 Plus in 3 different model configurations. And this is not even it. There's even a better way, because you can use here retrieval augmented code generation. I have a specific video on this, you know this, but just to show you this, how it works and what is the benefit of it, because of the way we built our transformer, about the architecture that is now different to a pure GPT system, let's have an example. So our query to the system is download an HTTP resource from URL and save to a destination capable of dealing with gzip compressed content. So write this code for this particular query of mine. Now, normally, if you have an autoregressive GPT system, it generates an answer. And it says, hey, yeah, download. And here compress, they look now for a Python function definition that has, for example, in its name, download and compress. And they say, hey, this is it. Now, this could be that just the name was chosen by some coder who has no idea that his code will be part here. And this is not the right answer. Because if you want the solution space this was searching in, it was so huge that they came up with a wrong solution. Now, if you have now an encoder stack in your transformer, you can have now that you first activate here the encoder stack and retrieve here relevant information. You remember in the human language case, it was this cosine similarity calculation that we did with vector representation. And now we can make the same methodology we apply here. We reduce the available space of all the different possible solutions, applying at first the BERT structure. We say, hey, look, I found this here with a high cosine similarity. And then, given my query and here additional data, I have here now retrieved here this, and then generate the solution, the coding sequence I'm looking for. And you see, now here in the definition of the Python function is some coder chosen here as a name download file. So only from the definition, you would not be able to guess that this is the right one. But as they write here, they were looking for here the URL lib3 command. And if you add here to this, the URL lib3 command, they found, there is exactly what we're looking for. So this methodology that is based on the architecture of the transformer that they use here in Code T5 Plus, with this step, they get a better performance here on smaller models, and smaller models in the open source community are really important. Ladies and gentlemen, welcome here to our coding session. You're not gonna believe it. We're gonna have now our inference run on a free Google Colab notebook. At first, we will install PyTorch. Then we will install the latest version of the transformers. We will go for dataset and accelerate. We will install bits and bytes and W and B. And this is it. And then the only program we're gonna execute is this little cutie here, transformer. We have a checkpoint from Salesforce, the Code T5P model. Unfortunately, the maximum size, we cannot use the 16 billion parameter, not the 6 billion parameter, not the 2 billion parameter model. We have to go on a free Colab notebook for the 0.77 billion parameter model. And we use a CUDA core. And I think we start now. So here we go. Torch, transformer. We don't need Taft. UTF local is required. Okay, there seems to be some problem. Disconnect, delete everything. Please delete everything. No, this is horror. Clear all outputs, runtime. Yeah, let's go. 1, 2. I need accelerate. I need bits and bytes. I do not need any login. This is the fine-tuning last time. Now we go for the Salesforce Code T5 Plus. Yes, ladies and gentlemen. So we have here the baby version. And you will see it will be able to run this on a free Colab notebook. It is exactly as you know it. Here we have a tokenizer, auto tokenizer from pre-trained. We have a checkpoint. The checkpoint is from Salesforce. Into the model, we have an auto model for sequence to sequence language model. It is a T5 model. You know it, you love it. Absolutely clear from pre-trained. We go with float 16 because we have this old NVIDIA GPU. Brain float is not possible. Forget about 8-bit. This model is not available in an 8-bit version yet. I hope maybe when you see this video, please try it out. And this is it, this is it. Then we have a look at the footprint of the model. And then, easy. We have a tokenizer, we have a Python function. The Python function is here, what I have prepared here. 4 examples for us. We go with PyTorch to device, we go on a GPU. And then we just go with the encoding of our input IDs. We have here the model generate command. I have the output set to a maximum length of 750 characters. And we decode the output, skip our special token, and this is it, ladies and gentlemen. So let's go for the first thing, and the first thing is very easy, a Python function that I defined here. And I say here in a text to code, remember, we have the BERT and the GPT. So here we have write a Python code for linear regression. And here we go, here we jump. Yeah, the other thing, is it finished? Yeah, everything's finished. Torch audio is finished, Hugging Face transform is finished, accelerate and dataset is finished, bits and bytes and W and B is finished. Yeah, everything is fine. So here we are now. So we are downloading here our tokens, our token map, our configuration JSON, and then we have here with 1.48 gigabyte our PyTorch model, this little baby model, our Code T5 piece. 0.77b. Okay, we have to take what we get for free. So, bene. This is the PyTorch model. And now, as you can see, we have a text to code ability. We have a code completion possibility. I will show you next. And then we can even go for a little bit more advanced thing. Of course, we're running now with a model less than 1 billion parameters. I'm really interested what result we will get back here from the free Colab notebook, but I wanted you were able to see this. You can do this on an iPad, wherever. Colab is great for experience to get here the first learning experience. And I'm still waiting for my first learning experience, and here we are. So you see, this is not the output. Write Python code for linear regression. So input numpy. Oh. matplotlib, so we have here a plot, then we have here our Python function linear regression, initialize the parameter, initialize the weight, intercept, it's a little bit complicated I would say, prediction, update the weights, what, linear regression with, okay, this is a little bit strange, generate some random data, fit the model with linear regression, okay, yeah, I mean, yeah, scikit would be available, but okay, and then we plot the data. But you know what? If we do it now the second time, you know, it's not always that the result that you are given is identical. So the model is now loaded, so it should be really fast to see this. It is real time. And then I can prepare already the next one, because next one I show you now here what here the classical models exceed here. If we give it here now a code sequence itself, here for a Python function, we say here the name of the Python function should be fit a linear regression model. This will then be our next exercise for the code completion. And now I have told you everything I know about these 4 lines of code. So now I hope we get a result, and here we are. And initial parameter, get some data. Okay. Well, yes. Maybe another possibility. Let's go here to the pure Python code completion exercise. This is where all the models shine. They do not have a BERT model attached or have not been trained on the chatty functions. So this is here more or less hardcore Code LLM. You have to give them here a specific Python function that you want, and you hope, you cross your fingers that the name that you're asking for somebody has used. Yes, here it is. Unbelievable. Here we go. Sklearn. Beautiful. So here we see you have fit linear regression, X and Y. We have a num array of shape. Y is a num array of this shape. From sklearn linear model, import linear regression. Yes, exactly. Fit regressor, return regressor. Easy as it can be. And the next one here is an example I would like to show you. This is a little bit more advanced. Write a Python code for an SBERT vector embedding of a sentence. And then I think you got it. You see, this is all that you need. Yeah, you can forget about the memory footprint because you see it. You have here those 4 lines, forget it. It is really just you define here the model you want to use. You define, if you go CPU, GPU, you have your tokenizer, your model, you have your encoding and the output. It can't be easier than that. So, beautiful. Yeah, if you have here quantization issues, there's an Hugging Face here, main classes quantization, advanced use cases for quantization. If you want to have a deep dive into quantization topic, but we stay here in the version that the model is available for us. So let's see what he knows about SBERT vector embedding of a sentence. And here we go. Hey, not so bad. Torch functional F, yeah. SBERT. Oh, wow, it defines now a class SBERT. Heaven's sake. Okay, we have our embeddings, we have the weights, LSTM. Wow, this is an old stuff. Linear, the weight, initialize the weight, the feed forward loop. Wow. Okay, I mean, for a model, for a baby model this size, 0.7, I mean, it hardly can see below, I don't know, above something. So yeah, okay, we have to be satisfied. But yeah, I would highly recommend that you have a PC infrastructure with an NVIDIA GPU that is able to handle this, because as I told you, just to show you, if I just change here this and I put here my beloved 2 billion parameter model in, you will see, yeah, at first the model is of course bigger. We have 6.45 gigabyte to download here our PyTorch model, but it takes about 2 minutes. Okay, we'll be back in 2 minutes, so that you will see we will crash with GPU RAM. So you can see it took us 2 minutes for 6.5 gigabytes. So the ant colony carrot single-handedly carry here every single byte over to me. Jesus. Okay. And now we are waiting. So our prompt is I write Python code for an SBERT vector embedding of a sentence. And I wanted to show you that maybe we are crashing. Oh, we are crashing on system RAM. Interesting. So let's see where we are crashing, for what reason. And as you can see, we had 11 gigabyte system RAM, available at 12. So I expect we will crash now any second with a 2 billion parameter model in a free Google Colab notebook. Yeah, as you see, 12.0, 12.7. My goodness, this is your session crashed. Restart after crash. After using up all available RAM. Yeah, come on, pay for Colab Pro. No, I'm not gonna pay, but I'm sure that you understand how to code it. Have fun with this. Experience this on your machine. So here you have them, more or less. If you want to compare here the Code LLMs, now here we finally finished here our selection with the Code T5 Plus, a complete different architecture that was also instruction tuned. The main model is the 16 billion parameter model, so really comparable here to our StarCoder 15.5 from Salesforce, here the open community from Hugging Face. But the nice thing is they give you here, if you want to try it out, a 6 billion parameter model, a 2 billion parameter model, and there's even a model below 1 billion free trainable parameter from Code T5 Plus. Now, to be realistic, everything that is in technical preview we have to exclude, and we have seen the results from the encoder from the 6 billion parameter model from Facebook does not match at all with StarCoder for whatever reasons. So if you're interested, and this was the request by the community about StarCoder, but I would like to show you that there are other models that can be very, very important that you know about them, and they can even have a better performance based on the way they were constructed, and Salesforce provide here also an open license. And when I looked at all of these models side by side, and I wanted to show you now the comparison, I noticed them. Sometimes those models create just blah, blah, blah. Nonsense. You've shown this in the introduction. So what we do. The first step is now to understand why it happens that the model do not perform. And this is easy. Because constantly we update our code data understanding. Stack Overflow is typical where I learned 100 years ago my Python coding. And you see just it was asked a question 21 days ago, modified 14 days ago, and just some days ago they came up with a new code sequence that is much better, and we should use this now. Now this is great, but your model has been trained for a particular day, I don't know, May 2023, and this is it. And maybe the next official update of the model will be in some months, or maybe in 2024. When there's a complete new run to fine-tune the complete model with the new code updates. It is very expensive here to run here the complete model on the new data. So the question is, what can we do to update here the code knowledge, the code book, if you want, that is available on the internet? Yeah, if you look at it, with the human language, the NLP task, it was easy. Because the work from Shakespeare are not changed at all. This is a static block of information. Or if you go for some French literature or English literature, whatever you want. Now compare this to the dynamic development here in Python. So you see, not only is it not as clear as a human language, but the speed that the Python code base changes is amazing. And this brings new problems to an update. Now here we go. Second step. Now that we understand that the code LLMs work differently, they also learn differently. Now let's have a look at this in detail. So we have to dive a little bit deeper. I already told you we have here our transform architecture. We have here the encoder stack that looks at the complete sequence and calculates the relation between all the different tokens. And this is our BERT system. And for the GPT system, we have the pure decoder stack. The decoder stack looks left and predicts the next token. Beautiful. GPT has also the reinforcement learning from human feedback, the templates, and this is now an interesting path forward for us. because these templates here could be something that we could utilize. Now, remember that I told you the GPT utilizes a left to right causal autoregressive language modeling objectives. This is beautiful. And they now try to integrate a feature of BERT, and this is here in BERT, the mask language modeling objective. If you think back 2 years with BERT and SBERT, you had this mask language modeling objective. That was at first a little bit difficult to understand, but then we become really familiar with it. So those mask language model can condition on both the left and the right context to infill here the mask region. And this is exactly what they apply now from the big GPT models. They're models that they have trained for millions of dollars to have now exactly this functionality of the BERT system. So let's play with this. Let's play now at the GPT part of the decode stack. How can we create these templates for ourselves, or how can you do it if you're a company? Now, creating multiple code templates is easy, cheap. Either you can do it with humans or you can automate it. You can publish like 5,000 macro jobs on the internet, and every coder on the macro work platform that has access to the internet should produce 1 instruction of the Python code as a training examples, 2 examples per day for a week. And you see, easy in a week, you get 70,000 code instructions that form now your new training data set that are based on templates. So whenever you have a task like save a Panda data frame in a CSV file format or open a JSON file in Python, those 5,000 macro jobs create in a week already 70,000 instruction-based Python code, for example, if you focus on Python, training data sets. So the combinatorial set now of those 70,000, how you add it together, how you stack different commands together for different tasks is amazing. It creates our modular stack. And this feeds back here in the template structure. So we have here a perfect update. You can do this, I don't know, every month, every 2 months, whenever there's a new version coming out from, I don't know, Python itself or whatever. So this is one solution. Beautiful. Or, interestingly enough, if you go with the Code T5+, you can vary now the size of the encoder and the decoder stack particular for your task. And this is another beauty of the Code T5+ model. So how can we learn here our LLMs that are not performing so beautifully, that are smaller? This is not a GPT-4 system, but this system's about 15, 16 billion free trainable parameters. What we have bug fixes, we have Python updates, we have new functionalities are added to all our libraries. Some code is now out of date. We have new libraries coming in. We have updates of libraries, daily basis, weekly basis. There are now better ways to code. Some gorgeous coder publish here very intelligent way of coding new sequences. You have new models. You have unbuilt. The dynamic is breathtaking. So good news. We have solutions for this. Yeah, yippee! And we have 2 solutions for you. So let's have a look. At first, those small 16 billion parameter models, you can fine-tune them. And I showed you at the beginning how to fine-tune system. And the good thing is it's a transformer system. We know how to fine-tune transformer. If you have a high-quality data set, and I would say this is the most crucial part, you can instruct fine-tune it. You can fine-tune it in a supervised way. This is the way to go. I will fine-tune my 16 billion parameter models for my specific code preferences. And you remember that I told you in one of my last video, this fine-tuning way, the way we build instruction fine-tuning templates, we can use now also in these huge monolithic GPT-4 models, or this Copilot X models that are based on GPT-4 in the prompt design, in the prompt engineering, in the templates we will use. Because this augmented additional information we provide in the prompt for the system based on in-context learning, and we have the instruction prompt templates that focus more or less exactly on the same fine-tuning technique. So this is great. You might say, hey, all this talking you had about jacks and flags, and is there anything to it? Well, if you're interested, this fine-tuning is, of course, faster with functional programming, and you can get some significant speed improvements if you want to enter here functional programming, but it comes here together in a beautiful way. And if you look at the current code examples, they all go with the functional programming approach. And if you go here with the prompt base or the open API base with our monster GPT-4 models, you have to ask yourself, hey, when is our prompt that we input strong enough to override the inherent knowledge of the system? Because the GPT system has been pre-trained and fine-tuned on millions and billions of code sequences. So if I have now a code update, I have to override the inherent system memory of GPT-4. When will it happen? And we have an answer for this. In one of my last videos, yes, exactly this, I showed you when it happens. Just let me go here, 4K. G. Remember, I was here with the learned content A inherent to GPT-4, and I said, hey, when does the prompt content override it? If the system content is our sun is a star, and I want the content our sun is a stone, when will this happen, and how do I have to design the prompt that now my ICL prompt content will override it? When is my prompt strong enough to override the system? And the solution you'll find here in this video, I don't want to go into detail. No, not at all. You know it. But we have now found two solutions. Either you go with the fine-tuning your Code LLM model with fine-tuning or instruction fine-tuning once every week, every month, whatever you want, on those beautiful open source 16 billion free trainable parameter models. This can be done nicely. This is within the budget that we can afford in our cloud compute infrastructure. Or if you want to use the power, the real power, the coding power of GPT-4 models, and you want somehow to override their knowledge, and you are not a system administrator in Microsoft Azure or the responsible for running the GPT-4 models on Microsoft Supercomputer Center, then as a simple user, you can, in every session that you start with GPT-4, you can have a prompt design to learn the LLM specific code sequences you want to use. You want that the system responds with when you want help for your coding exercise. So these updated code sequences, we now know how to insert with a prompt in our huge monolithic GPT-4 models. So we have two solutions. Fine-tune it, the smaller ones, and the same technique is working here with our prompt injection. Isn't that beautiful? We have two solutions to optimize our models, and I'm looking forward to what will happen in the next weeks, in the next month to come, because this is an area of research that is evolving with lightning speed. I hope it was informative. I hope you have some new information for your particular task you want to code. And maybe I see you in my next video.